So the next lesson is on the acid dissociation constant, which is what we use when we're dealing with weak acids. Because with strong acids, we can easily say that the hydrogen ion concentration is very simply related to the acid concentration, but that's not so with the weak acids because they're not fully dissociated. So instead, we have to use the acid dissociation constant. So firstly, in this lesson, we will want to construct an expression for the dissociation constant for a weak acid, including units. As well as that, we will want to perform calculations relating the pH of a weak acid to the dissociation constant and the concentration. And then lastly, we will want to know that the pKa is equal to the minus log 10 of Ka. So what is the acid dissociation constant? Well, put simply, it's just another equilibrium constant, but for a specific situation. And that situation is the equilibrium between for weak acids. And what we can do is we can take a normal equilibrium expression and simplify it such that it allows us to calculate the pH of weak acids. So let's do that. Okay, so acid dissociation constant, Ka, is derived from a generic weak acid equilibrium. So let's take the weak acid, which we'll call Ha. That's aqueous. That is in equilibrium with its proton and also the base. And what we know about weak acids is that mostly the acid molecules stay whole. There's only a tiny bit of dissociation. But nevertheless, let's write an expression for Ka. Right, so Ka is going to be the concentrations of the products, which are H plus and A minus, to their molar amounts, which are both 1, so we'll leave them off, and also divided by the concentration of the reactant on the left, which is Ha, also to the power of 1. So there is our expression for Ka, a normal equilibrium expression, but we can simplify it in a couple of ways. What we can do is we can let's just specify the concentration of Ha at the start of the reaction, and then also specify Ha, concentration of Ha at equilibrium. Okay, so normally, if with a reasonable amount of dissociation, you would get Ha dissociating into the proton and the conjugate base, such that these would be different. However, for weak acids, the dissociation is so little, there's so little dissociation that what you can say with a good degree of confidence is that the concentration of your weak acid at the start is the same as the concentration of your weak acid at equilibrium. So strictly, this expression should be the concentration of the acid at equilibrium, but what we can do is we can say, because the concentrations are the same, you've got the hydrogen ion concentration at equilibrium, you've got the conjugate base concentration at equilibrium, and you can say that the acid concentration at the start. So you can use the starting equilibrium concentration in your expression for Ka, and so that is the expression that you should remember. And we can simplify this expression one step further for weak acids. So I'm going to actually write that down so that I emphasize it. So for weak acids, I'll even underline it. So just for weak acids, what we can say is that our hydrogen ion concentration, right, at equilibrium is the same as our A- concentration. So what that allows us to do is to simplify this equation for the acid dissociation constant one step further. So Ka for weak acids can be written as the hydrogen ion concentration squared times the acid concentration at the start of the reaction. So next what we'll do is we'll look at an example where we can use this to find the pH of weak acids. So here's an example for us to work through. We're going to find the pH of a 0.02 mole per decimeter cubed solution of propanoic acid, a weak acid, formula given there, at 298 Kelvin. So Ka for the propanoic acid at this temperature is 1.3 times 10 to the minus 5 moles per decimeters cubed. So let's get in a helicopter for a second and just consider what the question is asking us for. So the question is going to ask us for the pH. So that usually means that you're going to use the equation pH equals minus log to the base 10 of the hydrogen ion concentration. So that's going to be the end point. But in order to use that equation, we're going to need the hydrogen ion concentration. And for that, we're going to use the expression for Ka. So let's start with that. Let's start with the expression for Ka. So we've got Ka, and it's a normal equilibrium expression. So we've got the hydrogen ion concentration. And we're going to times that by the conjugate base concentration, which we'll write like this. Okay, so that is the other product in the equilibrium expression. And the denominator is the reactant, which is the acid particle, the propanoic acid. And so we'll write that like this. Propanoic acid at the top. And it's a weak acid, so we're told that it's propanoic acid, and we know that's a weak acid. So we can simplify this to the H plus squared version of the expression for the acid dissociation constant. So it's H plus squared over the concentration of the acid. Like that. Okay. Now, what we're going to do is we're going to rearrange this, because really what we want is we want the concentration of hydrogen ions. So let's rearrange that to give hydrogen ion concentration on the left. Alright, so, well, let's do it in two steps. So we'll leave it, hydrogen ion concentration squared is going to be Ka times the concentration of the acid. Like that, because we've multiplied both sides by the concentration of the acid. And so therefore the hydrogen ion concentration, right, is just going to be the square root of Ka times the acid concentration, where Ka is given in the question, so that's 1.30 times 10 to the minus 5, and that's going to be times by the concentration of the propanoic acid. So we're given that the starting concentration is 0.02 mole per decimeter cubed. And if you remember, for weak acids, we can also assume that that is the equilibrium concentration. So we can write in here in this expression 0.020. And then when we feed that into our calculator, we're going to get 5.10 times 10 to the minus 4 moles per decimeter cubed. There. So now we've got the hydrogen ion concentration, we can use the standard pH equation, which you'll remember, pH equals minus log to the base 10 of the hydrogen ion concentration. Okay, so it's minus log 10 of 5.1 times 10 to the minus 4, which works out at 3.29. Done. So one of the other types of calculations we do on weak acids is to find the concentration of those weak acids. And so we've got such an example here where we are given the pH of the weak acid, 3.2, and we're given the Ka of the weak acid, 1.75 times 10 to the minus 5. And instead, what we have to do is we have to calculate the concentration of the solution. Let's just be quite clear what they mean here. When they say of the solution, then that's asking us to find out the concentration of the CH3COOH, the ethanoic acid concentration. So that's what we're going to do. Now let's just again get in our helicopter again. So if we're going to work out a concentration of the acid, it's likely that we're going to need the concentration of hydrogen ions, and in order to find the concentration of hydrogen ions, we are given the pH, so we're going to use the other form of the pH equation, the exponential form. So let's start there. Let's start by working out the concentration of hydrogen ions. So our hydrogen ion concentration is equal to 10 to the power of minus pH. pH we have been given in the question. So the hydrogen ion concentration is 10 to the minus 3.02. And that works out at 9.55 times 10 to the minus 4. And it's a concentration, of course, it's moles per decimeters cubed again. So now we have the hydrogen ion concentration, and if it was a strong acid, there would be some simple relationship between that hydrogen ion concentration and the acid concentration. But of course, this is a weak acid, and so instead, what we have to do is we have to use the acid dissociation constant instead in order to get from the hydrogen ion concentration to the acid concentration. So let's write an expression now for the acid dissociation constant. So Ka is going to be the concentrations of our products, which are H+, and that's part of the dissociated acid molecule. The other part of the dissociated acid molecule is written like this, and the reactant in our equilibrium expression is CH3 all to the powers of 1, and of course it's a weak acid, so we can use a simplified version of the acid dissociation expression, which is concentration of H+ squared over the concentration of the acid. Like that. Now let's just remind ourselves what we're trying to find out. As we investigated at the start, that's what we're trying to find out. Okay, and we've already worked out the hydrogen ion concentration, and in the question we are given the acid dissociation constant. So now we have 2 out of 3 of the variables. So why don't we just rearrange this expression so that we can find the acid concentration. So if we multiply both sides by the acid concentration and then divide both sides by Ka, we're going to end up with CH3 COOH concentration on its own, and we're going to have H plus squared divided by Ka. And so now all we're going to do is we're going to substitute in our values. So our hydrogen ion concentration from above is 9.55 times 10 to the minus 4, but that's all squared. And our Ka from the question is 1.75 times 10 to the minus 5. And we're just going to plug that into a calculator, and the answer pops out at 0.0521. It's a concentration, so it's moles per decimeters cubed. QED. So another type of calculation that we do with weak acids is to find the Ka of the weak acid. And we're often given the pH and the concentration, and we're asked to find the Ka. And such an example is given here. We can see that a solution of 0.162 mole per decimeter cubed of hydrogen cyanide has a pH of 5.05 at that temperature. What is the value of Ka for hydrogen cyanide at that temperature? So we're going to end up using the expression for the acid dissociation constant. If you remember, that's the concentrations of the hydrogen ion squared over the concentration of the acid. That's what we're going to end up doing, but in order to use that, we're going to need first to work out the hydrogen ion concentration. And you notice in the question we've been given the pH, and so that means that we can easily calculate what the hydrogen ion concentration is. So let's do that to start with. Okay, so we're going to use the expression hydrogen ion concentration, right, equals 10 to the minus pH, and 10 to the minus 5.005, that is. And so that gives us a hydrogen ion concentration of 8.91 times 10 to the minus 6 moles per decimeter cubed. Okay, so already we've got that. And so we can feed that straight into the expression for Ka. So let's write our expression for Ka down. So if you remember, we're going to have the hydrogen ion concentration as the first product. And in this case, it's going to be, the conjugate base is going to be Cn minus as the second product. And the acid concentration is going to be on the denominator. So that's our expression for the acid dissociation constant, and it's a weak acid. Hydrogen cyanide is a weak acid, so we can simplify that to hydrogen ion concentration squared divided by acid concentration, like so. And we are given the starting concentration of the acid, and as we know, for weak acids we can assume that it's also the equilibrium concentration. So we have this, and we've worked out hydrogen ion concentration, and so all we need to do is to feed those in, and we'll find the answer to the question. Let's do that. So from above, we can see that H plus concentration is 8.91 times 10 to the minus 6. We're going to need to square that. And from the question here, we can see that the HCN concentration is 0.162. When we put that into our calculators, we get 4.90 times 10 to the minus 10 moles per decimeters cubed are the units for Ka, which is worth remembering as it happens. The other thing I'd point out before we move on is to look how awkward these numbers are. 4.90 times 10 to the minus 10. And in the previous question, the Ka that we were working with, if you remember, was 1.75 times 10 to the minus 5. So pretty awkward numbers. And that leads us on to the next and final topic for this video lesson. So that leads us on to the logarithmic constant, pKa. So that is just the acid dissociation constant made into a form where the numbers are easier to work with and a bit more intuitive. Because the reason why we want to do that is just as hydrogen ion concentration varies massively from one acid to the next, so does the value of Ka vary massively from one acid to the next. So what we can say is that pKa, where p is just the minus log to the power to the base 10, so pKa is minus log 10 of Ka. And when we take the minus log of Ka, we get much more reasonable numbers, just like we do with the pH scale and hydrogen. So that might be worth actually writing down. So pH is minus log 10 of the hydrogen ion concentration, just as pKa is the minus log 10 of Ka, because both hydrogen ion concentrations and values of Ka are odd numbers, so we take the minus log 10 of those numbers to make them more intuitive and easier to handle. So we now have an expression for pKa, and the corollary of that expression is, of course, in the same way as with pH, Ka is going to be 10 to the minus pKa. So if you're given one and need to find out the other, you're going to use either one or the other of these two equations. So let's work through an example. Let's say we have some methanoic acid. So let's write that out. Methanoic acid is HCOOH. Let's say we have some methanoic acid, and it's at concentration. The concentration of our methanoic acid is 0.05 mole per decimeter cubed. And what we want to know is what the pH is. And we are told, as well as the concentration, we're told that the pKa is 3.75. Notice, a much more intuitive number. So if we're told the pKa is 3.75 and the concentration of the acid is 0.05, what is the pH? So actually the first thing we have to do is to take this pKa and convert it into a Ka, because then we will be able to find from that the hydrogen ion concentration, and from the hydrogen ion concentration we will eventually get to the pH. So we know from left that pKa, that Ka is 10 to the minus pKa, and we're given 3.75 as pKa, so it's 10 to the power of minus 3.75. So Ka comes out at 1.78 times 10 to the minus 4 And remember, the units of Ka are mole per decimeter cubed. Right, so now we have Ka. We can use that to find the hydrogen ion concentration using the acid dissociation constant expression. So just moving left, we're going to now write down the expression for the acid dissociation constant, which you remember is the hydrogen ion concentration times the conjugate base concentration. So we've got HCOO minus. There would be the two products in the equilibrium reaction, and the acid would be the reactant in the equilibrium reaction. So we have the concentration of the acid remember, it's methanoic acid. So that's our expression, and as usual we can simplify that for this weak acid. So we're just going to write this as H plus squared divided by the acid concentration. And we're given the acid concentration, and we've now worked out we've worked out Ka. So we can work out the hydrogen ion concentration by rearranging this equation. So we're going to have hydrogen ion concentration is going to be the square root of Ka times concentration of methanoic acid. Like that. I've just done two steps in one there. I hope you can see what I've done. So we're just going to feed our values in here. Ka we've worked out at 1.78 times 10 to the minus 4, and the concentration of the acid is 0.05, and we're going to take the square root of that sum, and that's going to come out at 2.98 times 10 to the minus 3, and it's a concentration, so it's mole per decimeter cubed. So now we have the hydrogen ion concentration, and from there it's relatively easy to get the pH. So we're going to use the usual expression. So our pH is going to be our minus log to the base 10 of our hydrogen ion concentration, which is 2.98 times 10 to the minus 3. And that works out at 2.53. Done. So let's just check off that we've covered off our learning objectives. We were to construct an expression with units for the acid dissociation constant, and so you'll remember that that is concentration of H plus, let's call it A minus, over HA. Right, and that can be simplified to H plus squared over HA. With HA, we're allowed to use the starting concentration because it's a weak, almost undissociated acid. Okay, that was what we had to start with, and then we're going to perform calculations relating to pH. So we often use pH equals minus log 10 of the hydrogen ion concentration. So we're going to relate the pH to the dissociation constant, the expression for which is above, and the concentration of the acid. So we've done various versions of those, and we've also done a calculation that involves pKa instead of Ka, with slightly easier to handle numbers. Okay, that's the end of this video lesson. I hope you've enjoyed it. I hope it helps.